Hello, my name is Bogdan.
And my name is Roshan Korai.
We are both students at the Military Technical Academy in Cluj.
And together we made this project that found the road.
This project consists of a remote control and autonomous rover. When we designed this project, we established as main goals surveillance and exploration. Our robot gathers from the field information, and this information is displayed with the help of a companion software application that runs on a laptop to the operator. This application shows various information like GPS location, ambient temperature, battery charge level, radio link quality, altitude, heading, and camera images. And when I refer to altitude, I refer to the pitch and roll angles. Our robot can be controlled with the aid of a joystick or a smartphone.
You may wonder why we chose this project. First of all, it presented a huge opportunity to learn not only robotics, but programming, mechatronics, and others. Second of all, most of the available designs on the market are overpriced, the source code is not given, and similarly present an educational interest. And last but not least, we wanted to fulfill our teenage dream to create a smart remote controlled car.
The rover presents a series of features that help the operator to fulfill a remote surveillance mission. For instance, the rover has an onboard camera mounted on a panel tilt mechanism, and it can operate in two modes, manual and autonomous. When it operates in manual mode, the rover can be controlled with the aid of a joystick or smartphone. When it runs in autonomous mode, the rover can follow a set of different waypoints. Also, our robot has the capability to respond in real time, and it consists of an independent system with minimalist software and peripheral requirements. Another important quality of our robot is that it is easy to be relocated and quickly assembled.
This is our systems diagram. On the left side, we can see the robot equipped with a GPS module, a radio module to establish a communication link with the control station, and a wireless video transmitter to transmit the captured video.
The control station. The control station consists of a control station application that runs on a laptop and the control unit. As we can see in this diagram, the central element of this system is the laptop. The laptop acquires data from the joystick and from the smartphone and transmits it to the control unit through the Ethernet or serial interface. The joystick is plugged in directly into the laptop, and the smartphone, which is an Android-based smartphone, communicates with the laptop to Wi-Fi. Also on the laptop are displayed images captured with the aid of the image acquisition board. The control station application was designed in Qt framework, and it employs a multitude of application programming interfaces. For instance, we used OpenGL to simulate the robot's position. We use OpenCT to implement facial detection algorithm. We use direct show to get the images captured with the aid of the image acquisition board. And we also use the Android software development kit for the application that runs on the smartphone. Our control station application has the following main features. It's easy to use because the operator not only establishes the communication type with the control unit and it's ready to go. It has a dynamic interface because the operator can configure his workspace and display only the information that he needs. Because it was designed in Qt framework, it's a multi-platform application.
Yes, display. Hide the hardware complexity and to avoid the misconfiguration of the hardware peripherals. As you can see, the hardware abstraction layer sits on top of RealTOS and microchip peripheral library. Another library, microchip special IP stack, was used to achieve the Ethernet connectivity.
We figured out that in order to achieve reliable and easy to use data transmission, we had to implement communication protocol. You can see an example of our data encapsulation process. When the operator wants to send a command, we send the data to the application layer, which adds an operational code header. Then the data is passed to the data link layer, which adds a sync header and a payload length. On the third figure, you can see an actual example of an operational code that sets the rover navigation.
H-bridge module to 4 H-bridge modules. A PMOD TMP to sense the temperature, which is sent back to the control unit, then displayed to the operator, which includes the GPS position, both and local position, attitude and heading, ambient temperature, and the live video stream. Implemented. In figure 1, you can see a typical payday control loop, and in figure 2, we can check the radio link to see if we have any dropped packets. Please shut the robot down so you can actually see. The control unit sends packets, but they are not acknowledged because the robot is not operational. Okay. This is the actual robot simulated in OpenGL.
You can see a tilt compensate algorithm, which allows the camera to remain in the given position.
This position is controlled with the joystick. Put the video camera to the side. Capture camera. Pretty difficult with this low resolution. I'll put a higher refresh rate. The interference is caused by nearby 2.4 gigahertz routers. We also have face recognition, which can be activated by clicking this checkbox.
I will turn on the light.
Maybe it works without that. It's actually pretty CPU intensive, hence the low frames per second. Okay, and I can demonstrate the manual control with the joystick. And to demonstrate the smartphone control capability, I will ask my colleague to plug the connecting.
the smartphone communicates with the laptop through Wi-Fi, and the colleague must communicate with his laptop's IP.
It seems like he hasn't acquired the GPS fix because we are in a room. Not fixed. We'll try to get it outside to see if we can acquire a GPS fix. Let me tell you my IP address.
In one of the breaks. Install it outside.
Okay, it seems like that we have a technical glitch. The router is not working. To demonstrate the local map navigation, we implemented the local map widget. This widget is simple to use. You simply right-click in the position that you want the robot to navigate, like this. Choose adding waypoints. For example, this point is located on the y-axis at 85, which equals to 85 centimeters in front. I would like to invite you outside to demonstrate this. Because exactly.
Okay. You said that for the first coffee break. If we go outside and come back
during the coffee break.
Okay, we'll just take the robot outside and we could watch it from inside.
Okay. So anyway, I think just one more minute to just to wrap up things and reach the conclusion, and then you can take it outside and
okay.
Just to start the next presentation. Okay.
Okay. Merge? Sure.
Control the robot speed and direction.